All right. Thank you.
Yeah.
May I
Okay.
start?
Yeah.
Or you want to?
Go for it. Yeah.
Okay. So my name is Pedro. I am a graduate student both at Purdue University and at the Federal University of Rio, back in Brazil. And today I'm going to give a talk about this package that I am the main developer called Cubo.jl. But this time I'm going to give you an operations research user experience perspective. So what is Cubo.jl? First of all, what is Cubo? So Cubo, as many people here might be familiar, stands for Quadratic Unconstrained Binary Optimization. And it's the main mathematical framework through which many of the quantum devices and also other physics-inspired devices have been communicating. So many of them are capable of addressing this specific mathematical formulation. In a certain case, because it is the simplest non-trivial mathematical model, so to say, because you have only binary variables, you have no constraints, and your objective is quadratic, because if it was linear, it would be too simple. So it can, in fact, encode many types of problems that are known to be NP-hard. So this package, Cubo.jl, it has a lot of stuff going on. It has a common interface in JUMP for these many different solvers to be operated. So in a certain sense, allows people to access quantum devices through JUMP, which is super fun. On the other hand, it also allows people to translate more complex mathematical models into the Cubo formalism, and then it goes to the device. So this also allows us to do some systematic benchmarking and compilation that is directed to the architecture. So going forward with this, there were many talks about Cubo.jl before, explaining how we can draw parallels between its tools and some other compilation tools and passes and everything that goes behind. We also discussed how mathematically this happens in other JUMP dev and JuliaCons, and also how this really happens and more advanced things that are going on behind. And also, it's the fastest thing around and one of the most comprehensive tools for doing these things. But today I want to talk more about user experience and a little bit of the history of how Cubo.jl was developed and how we can how we can think about the field as it's evolving and other related tools. So I'm part of the operations research area, and I spent some time in the industry, especially working with power systems. And at some point, we started interacting with people who develop quantum hardware and also people who are into algorithms that are either inspired by quantum or also address the same kind of problems. And in another Thursday in the office, I was thinking about this problem where you have to plan the power plants you're going to build and you have to operate them. And we usually write it down. As you can see here, you have some operation costs, investment costs, unit commitment, and constraints going on. And usually we just write this in JUMP, and it's very similar on how you think mathematics and how you write code. And this is something that if you think, if anyone here was in the OR tools talk earlier before, the great thing about mathematical programming is that it's above all a language in which we can express ourselves. You just define problems. You don't care much how they are solved, but people are used to. So whole industries rely on being able to express ideas through mathematical programming. And this company I was working for was very deep into research. Actually is pretty much part of the JUMP community still up to this date. And my boss just asked, how can we run this on quantum devices? And ideally, what we wanted to do is that we could change 2 lines of code and be able to run it directly. So this was the dream back then. On the other hand, we started interacting as the project went on, and we started interacting with other companies that were developing all those tools, and we faced a very heterogeneous landscape of devices. So we had quantum machines, we have math-heuristics algorithms that were also compatible with the QUBO formalism. We even developed more recently a solver that is based on iTensor to use tensor network algorithms for solving QUBOs. And interfaces usually adopt all different conventions you can think of. Some of them want Ising models, some of them want QUBOs. They have different installation methods, programming language. Just this part just reminds me of Python interoperability all the time. And you have different data formats. Some of them give you results in an asynchronous manner. Some of them give you that straight away. And on our sides, much of my colleagues that were not that much interested in quantum or learning about it, it was just too much, right? So this is where really Cubo.jl stands out. So we were able to get all those things that were going on and organize them very straightforwardly into JUMP. And suddenly you had complete access to all these devices in the same manner that you used to do before with your regular solvers, let's say Gurobi or Hive or something in that sense. So now we have the same interface. You write the same code for D-Wave, for IBM machines, for parallel tempering algorithms, and new machines were dropping as the project was evolving. New devices came up, and we were able to rapidly integrate them because if for the user, it's now very easy because they're used to running models in JUMP this way. For algorithm developers and hardware manufacturers, the code for integrating this into the JUMP ecosystem was just this. So this is actually the real code, the one that is being used for the D-Wave integration. And you have a macro to set up all the math-opt interface boilerplate and some other code telling you how to sample those results and organize them. And that's it. So this is all you need to have your solver integrated with JUMP. Naturally, as soon as you have this whole collection of solvers that we could use right away, testing them automatically and benchmarking them was just the next step. So we came up with a library for organizing all these instances of different QUBO problems, and this led us to a partnership in the IBM Quantum Optimization Working Group that led to a paper, to another benchmarking library. So in this sense, it was very successful. And everyone was happy, right? So both device developers and people who are used to just setting attributes and calling optimize were now all able to access quantum machines. And we delivered some summer courses on this in different universities, and students, they just got their API keys and just started running the models. They have if you just search for QUBO notebooks, there are many notebooks that make using quantum devices as easy as this. So in summary, we started with our goals were just to have a common interface and a compiler that allowed us to run more complex problems, such as the one for operating power plants. And this led us to some questions forward. So how can we pick the right solver, and how can we choose the best way to reformulate a problem? And this led us to benchmarking, and benchmarking led us to have a library. And currently, we are giving our steps beyond QUBO, because this whole thing of having an interface that makes it so user-friendly and accessible, I would say. And more than that, when people usually think of optimization as being a killer app for quantum and something that people say it's going to be advantageous as soon as possible, and that should be something people should be interested into. And we look at how people actually do optimization out there, the interfaces, they are very, very apart. So if you look at the regular pipeline for operations research and how you expect your problem to be passed and results to be analyzed later, there is a gap in between that keeps experts in the field from really thinking about this problem and how to use novel devices. So as soon as we started bridging this gap with our software and got more and more attention, we also went beyond Cubo, and some manufacturers that develop hardware that are capable of not only binary but also integer and misinteger problems also approached us, and this led me to do some internships that in other companies that were interested in this, and this led us to an expansion and made also our Cubo tools way better. So what I wanted to say in the end is that for optimization to really be something, and for us to understand the relevant problems that need to be benchmarked, we need to get closer to the community that has been doing this for a long, long time. Because much other problems that we usually see as being the ones that are first approached by Quantum are very classical computer science problems, so to say. And I feel, so this is the take I want to get with this presentation, is that we should be closer to people doing the applications that move very heavyweight industries all around. So I would like to thank my collaborators that started the project at PSR and at the Federal University at Rio, and now that still work with me at Purdue University, and my colleagues at Microsoft that were responsible for taking this project also to other formulations and to the machine that they've been developing. That is a photonic machine that's quite interesting, and for being such supporters of Julia and using this in the whole pipeline of the novel machine that they brought up. Thank you.
I think maybe for sake of time, we should maybe have questions offline. We could do like maybe one quick question, and then, yeah.
Were there any machines on which, quantum machines on which these actually were executed and showed something that was better than the best classical tools in Jump?
So, sorry. Okay, the benchmarks. So the benchmarks, they were run only in comparison, so they all use Jump, because what happens that most of the benchmarks that we've seen before, they were from a single manufacturer on a single problem or just a few problems, and they're like highly biased towards either problems that are well-known in literature or the ones that work very well. And with this work, we are able to put this benchmarking up to scale in two senses. One, that we have one of the strongest reformulators in the market. So in this IBM paper, we were able to generate very large instances and different instances of different types. And in the other sense, since they're all connected to Jump, we don't have the same situation where you have a paper with two different devices competing. We now have dozens of devices competing. So, but this is not focused on, at least not talking the reformulation side, on getting the best of the performance of the solvers. We're providing the way for hardware developers and algorithms people to basically fight each other under a common ground.
But the quantum folks, did they win anything in that fight?
No,
the quantum folks, did they win anything in that fight?
I have no news about that, yeah. Like, never heard of any quantum really winning. I think, yeah. But something that's very important, and we cannot just underestimate that, is that great advances in the hardware side have been happening over the past like 5 years. The advances are great, and this is a very nice way to keep track of how things are evolving with time. Like the amount of data that we generate at each time slice that we run our benchmarks is the coolest part of it.
All right. Well, I think at this point, we'll take any extra questions offline, and we can thank all the speakers for the session. And I think this closes all the quantum talks. So yeah, big round of applause to everybody who's here for the quantum talks.